Thank you very much, Professor Santos. So as you can see, the topic of my talk is what do baggage handling and mRNA have in common? Object process methodology in service of science and systems engineering. Hopefully, by the end of the talk, you will be able to take the short quiz and answer the question. So let's start with the various languages that multiple engineering professionals talk. So we have mechanical engineers, civil engineers, electronics, electrical engineers, software engineers. This is just, as I'm sure you know, a very partial list. And so mechanical engineers have machine drawings as a language. Civil engineers have floor plans, among others. Electronics engineers have circuits diagrams, which this is a manifestation of the materialization of. And software engineers have software models. This happens to be a UML, Unified Modeling Language, class diagram, a simple class diagram. But there are also one brand of engineers that are fairly new, systems engineers. What language do they talk? Actually, the situation is even worse. We only have been looking at the developers and the integrators, the engineers that are involved in developing a product. But there are many other stakeholders, such as the project manager, the customers, the regulators, the testers, the vendors, and they all have to relate to the same system or product that is being developed and maintained. And what language do they speak? Of course, they speak natural language, but is it good enough? Digressing a little bit aside, because I want to tie it later on to the topic of the talk, I want to devote a couple of minutes to my view on biological research. As an engineer, I look at research in science in general and in biology in particular as reverse engineering of nature. So we have a system out there. It could be the human brain or a living cell, any other natural system, either biological or non-biological. And we want to try to understand how it functions, how it operates, what are the secrets that we can unlock behind it. So we carry out wet lab experiments, chemical, biochemical, and so on. And from that, we get research papers and that list and document experimental findings, which in turn gradually enable us to combine a puzzle of what this elephant looks like. So we want to build a conceptual model of the biological system we are investigating. And of course, there are several pieces always that are not in place. And we have some new conjectures about what these pieces are and where they might be able to fit. And in order to do this, we need to carry out additional wet lab experiments. However, these are highly expensive, time-consuming, and often also hazardous. So just bear this slide in mind as we come back to it later on. We as humans are used to use pictures, spoken words, and written words as we communicate. And we convert data, which is just raw information, into knowledge, which is processed information. And we process it using words and pictures simultaneously in our brain. But if you compare the speaking, either written or verbal, to processing of images in the brain, it is not difficult to argue that from an evolutionary viewpoint, the human brain has been trained to capture and analyze images much earlier, orders of magnitude earlier than the development of spoken and let alone written language. Because people and as biological creatures had to survive, so they had to escape predators and capture food in order to survive. And vision is really the best way to do it, maybe the only way. And so spoken words and text are very recent. So you can think about, even if you take 10,000 years compared to several hundred million years of evolution of biological creatures, that they are not even a tiny fracture of a percent in terms of time. And so this is really in our brain a much more modern and external, if you will, add-on to what used to be our old brains. Therefore, pictures are much more appealing intuitively and graphics to the human brain than spoken words. However, with spoken language, we can express ideas that are far more complex and often impossible to express graphically. So this is why we use both modalities, the pictures and the graphics, the pictures and the graphics on one hand, and spoken and written words on the other hand. So this is a paper I published in Communications of the ACM a few years back, and this really talks about the dual channel processing that the brain operates. Is one of the three principles of the cognitive assumptions that have been also applied in multimedia learning. So dual channel processing asserts that humans process information in parallel through two channels, the verbal on one hand and the visual on the other. Then there is a second assumption that the human cognition is limited in its capacity, so that short-term memory can only hold up to 5 or 7 plus or minus 2. This has been known since '56 as Miller's magic number. Recently, this number has gone down from 7 to 5 and maybe 4 plus 2 minus 2. So, and the third cognitive assumption is active learning, in that people learn best as they are engaged actively in the process rather than, unfortunately, sitting like you are doing now and trying to absorb theoretical material. But that's tradition. So all this really points to the fact that a universal language other than natural language is really going to be very helpful in trying to model systems that are complex in the world. If all systems were simple, there would be no need for such language. But as we know, most systems that are of interest are highly complex, and in order to put our arms around them, we really need a language that is both visual and verbal and will be at the same time formal enough to be able to be checked, and at the same time intuitive, so that it's not remote from most humans' intuition. So here is a question for you. You see, I'm trying to engage you. What is a minimal set of concepts needed to describe the world or part of the world, subsystems of it? If I ask you to give me 2 types of things or the minimal set of concepts, name 2 things. Okay? Shall I give you a hint? Okay, so what is out there? What is the world made of? Things, right. Things exist, right? So we call those things that exist objects, okay? Take it from me. But what other component is needed beside objects, which are things that exist? Processes. The things that act on the things that exist, on the objects, and change them, transform them in some way. So you pass the test. So the answer is that things that exist in the world and things that happen to those things that exist, okay? And So what do we call? You already should know the answer. What do we call things that exist in the world? And what do we call things that happen to them? Objects are the things that exist, and processes are the things that happen to the objects and transform them, change them in some way. Now, there is a question that you might ask, what do you mean by transform? And I'm going to answer this in a few slides later, so hold this question. Why do we need conceptual modeling in the first place, though? We want to construct a mental picture of the system that we are investigating. We want to anchor our understanding in some visual formalism for dual-channel processing that I mentioned. We want to design systems using non-verbal means that can be documented and tested and simulated. We want to convert tacit knowledge, things that we think we know, but we never express them in spoken words, to explicit knowledge that is documented, written, can be read and communicated to others. So we want to communicate this concept to others through explicit knowledge that is documented in graphics, in pictures, and in spoken and written natural language. So what is really required is a graphical language that has a textual, natural, yet unambiguous representation. The idea is that up until now, in the past and still ongoing, is that almost all of our documentation is in form of text. There might be, there usually is, accompanying annotations and diagrams and sketches that enhance the textual description, but basically these are textual descriptions and natural language text. And the idea is to move from this current state of affairs into a future where text, of course, still exists because this is the natural means of communication, but the text is grounded on some formal yet intuitive visual formalism, some kind of a model that uses a formal language that is simple enough, intuitive enough, yet can be mathematically validated and can be also scaled up. And this is needed for design, requirements, elicitation, alternative evaluation, system architecture, detailed design, testing, integration, deployment, use service. This is a typical list of a life cycle of a system and a product and a service too. And so we already spoke about the fact that the key to conceptual modeling is telling processes from objects. So if we recognize that processes and objects are the two key elements, in fact, the only two ones, as I'm arguing, we have the conceived reality. I'm saying conceived reality because we cannot talk about the reality in a manner that is not related to humans. We conceive reality through our senses. So we have, we only can see light that is within the visible range. And if we had X-ray vision, we would see the world differently. So this is why I'm saying conceived reality. We can talk about an airplane or a bus, or what is this?
Guy paying too much for gas.
a guy filling his car with gas, okay? Or maybe hoping to fill his. So what is the difference between the first two and the bottom one? Right, the bottom one is a process where we imagine something happening. So even though it is a still image, we can still think we have in our imagination a mental picture of something happening rather than something existing. You can also argue that this airplane, because it's in mid-air, it probably is flying rather than falling, which is also a process. But we don't know about the bus, whether it is standing or going. So this airplane is modeled by an object called aircraft. So objects are modeled by boxes with the name of the object in it. So this is an object. A bus, similarly. So an aircraft is a vehicle, okay? A bus is also a vehicle. So you can start seeing how we can generalize concepts. This, however, we said is a process, the process of gas filling. And it's a process, and it somehow affects the car. And gas filling is also some specialization or kind of energy replenishing process, okay? Which could be, if this were to be an electric car, then instead of gasoline filling, we would maybe be swapping batteries or recharging the battery. So we would have another type of energy replenishing process. So objects like processes are analogous in a lot of senses that we can talk about them as things. So rather than talking just about objects, which is what the object-oriented paradigm is doing, we now talk about things, whereas things can be either objects or processes, and they complement each other in the role of modeling systems. So the model expresses real things, objects and processes, and relations among them. So the things are objects and processes. This is how they are represented. An object is defined as a thing that exists. It can exist physically or informatically. And the process is a thing that transforms one or more objects. So in order for a process to be valid in OPM, it really has to transform one or more objects. So what do I mean by transforming? Remember, I promised an answer, so here comes the answer. Processes transform objects by three options. Option one is that they consume the object. The process consumes the object. So if we have a process called manufacturing, and there is raw material, the manufacturing process consumes the raw material object. Now this is a screenshot, a part of a screenshot of a software that we developed called OpCat that is used to model OPM systems using OPM, modeling systems using OPM. And because we want to represent the model in two modalities, both graphic and visual, in order to enhance understanding and to boost the dual channel processing, this software automatically translates the graphical input into natural English sentences. So as soon as I draw this and link them together with this arrowhead, which graphically, intuitively means this process consumes this object, so you see the arrow goes into the process, I get this sentence. I don't type it. I get it. Manufacturing consumes raw material, okay? So consuming is one of the options for transformation. Creation, which is the opposite of consuming or destructing, is another option. And as you can see, we continue our model. We had raw material that manufacturing consumes. Now we have product which manufacturing generates or yields. And so as soon as I did this, I got the second sentence, which is manufacturing yields product. Okay, so we now already have two options for transformation of objects. The third one is changing the state. So now I'm introducing a new concept, which is called state. So far, I talked about objects and processes. Now I'm saying that objects can be stateful, can have states. So product, as our example, can have two states in this system, pre-tested and tested. And there is a process of testing which takes a pre-tested product and does something to it such that when this process is over, the product now moves to its tested state. And the corresponding object process language sentences, as you can see below, are product can be pre-tested or tested, the names of the two states of this object, and testing changes product from pre-tested to tested. You can now quite easily imagine how, while it might look like a trick or a miracle that a computer can write such English sentences, that it is really quite straightforward. There is a pattern here, and as soon as this pattern is recognized, by the system, it spits out putting the names of the states, the objects, and the processes in the right place, and adding the non-reserved words, if you will. So you can think of it as a programming language where you have your reserved words, such as can be, or reserved phrases. Can be, or, changes, from, to. These are the ones in dark, whereas objects are green and processes are blue, and states of objects are brown. Okay. Similarly, before we saw also this manufacturing is the name of the process, consumes is a reserved word of our quote-unquote programming language, and raw material is a user-defined variable, if you will, which is the object here. And you simply put a period because this is how English syntax goes in most languages. Okay, so we've seen the three options, or the three possibilities of transforming transforming objects by processes, generating, consuming, and changing the state. Okay. So we can go on now and see it in one diagram. We have three entities of OPM: things, which are objects and process. This is the object product, the process of testing, and state, pre-tested and tested, which is a situation an object can be at. So an object can be pre-tested or tested, and testing is the process that transforms product by switching it from its pre-tested to its tested state. And all the rest, so I'm promising there are no more entities. All OPM is those three entities. All the rest are several types, not so many, about 10 types of links among the entities. And my claim is, and it has been proven over the last 20 years, is that with this minimal set of concepts, we have been able to specify and describe and simulate systems at any level of detail, so at any level of complexity, and at any domain that we have attempted. Okay, so here is another example, a little bit more real-life example of a baggage handling system. Okay, so a typical system consists of a set of object process diagrams, not just one, but they are interconnected, and you can see on the left the hierarchy of the diagrams, and we'll see it in a moment. So you have baggage handling as the function of the system. What is the value that the system is supposed to deliver? Of course, here we are talking about man-made artificial systems. If it were a natural system, we couldn't talk really about value unless we would go into theological, philosophical debates. But for man-made systems, people don't put the energy and efforts to do systems just for the fun of it. There is some value expected to be extracted from that system. So we are talking about a baggage handling system whose major function is baggage handling. And there has to be somebody who benefits from that system. Who is he or she? It's depicted here, the passenger, right? So here is the system's function, what it does, and for what purpose. Here is the beneficiary, who is the passenger in this case. Then we also have the operand, the object on which the system operates to extract the value, which is the baggage. And that operand has an attribute of location, baggage location. And that attribute has two states, or two values, actually. So one of the values, we say value when it's a state of an attribute. So baggage location can be origin or destination. And the value of the system is to take a baggage from a location with value origin, do the trick, and change the state of the location of the baggage to destination. If it did it, it succeeded. If it flunked, then we won't find our luggage when we land in our destination airport, which I'm sure all of you experienced at least once. So this is the object process language text that was automatically generated. Now, just to show you that this is not just a PowerPoint slide, here is the real thing. And you see it moves. This is not PowerPoint. Moreover, I can show you, this is a little bit different from the slide on purpose. So here we have another attribute of baggage, which is weight. And so you can see that baggage exhibits weight is the object process language, the OPL, analog to the graphical representation of this symbol. So this symbol means that this is an attribute of this. Okay, but in the PowerPoint, I had that baggage location is an attribute. I didn't have weight. So I want to do this. So I'm clicking here, and I link it here, and I have to do it so that, OK, so I got it here. And what happened to the sentence now? Remember, we had the baggage exhibits weight. Now we have baggage exhibits baggage location and weight. Okay, so it didn't add another sentence on top of the baggage exhibits weight. It just added it, so it sounds more natural. Okay, back to the slides. So this is our object process diagram, the graphical modality of the model. And this is our object process language paragraph, which is a collection of all the sentences that together express in text exactly what is expressed graphically in the top part in the object process diagram. So I could, and I can actually, take the text part, which anybody from third class can understand as soon as he or she knows to read, and generate from it the graphical part, just as I'm generating the text from the graphics. And indeed, I can type sentences, and they will be reflected in the graphics. So it's bidirectional. Although it is much more, from a practical viewpoint, it is much more easy and tempting to do it from the graphic to text and not the other way around, because you have to remember the exact syntax, and if you forget the period, it will not know what to do with it, for example. So this example already shows the unification of the three aspects that the systems normally have, which is the function, namely why the system is built, what value it is delivering, the structure, the static aspect, what the system is made of, and the behavior of the system, the dynamic aspect, which is how the system changes over time. Okay? So if we go back here, the function is this, baggage handling. The structure is, for example, that the baggage exhibits baggage handling as an attribute, and that the passenger owns. See, passenger owns the baggage. We also have this sentence is somewhere up. It's hidden. And we see that the passenger is involved as an agent to this process, and there is airport and airline that are involved as instruments to this process. So they themselves don't change, but we won't have the system. We will not be able to carry out the function without the airport, without the airline, and of course without the passenger. So these are enablers. Enablers can be agents or instruments. Agents are simply humans or groups of humans, and instruments are anything that is an enabler that is not a human. Okay, so we express it bimodally in graphics and text that are equivalent and can be reconstructed from each other, and this is done in a single model. But of course, there is more in the baggage handling system than just saying this is a system. So okay, we want to start seeing the details. So there is a mechanism of refining this top-level abstract view of the system. So one of the options for refinement is in zooming. We zoom into the baggage handling system to see what sub-processes it consists of, okay? So what we end up getting is this diagram, this object process diagram. This is an elaboration. It is not contradicting the previous one, but it adds quite a number of details that were abstracted in the top level diagram, the system diagram as it is called. So what we see is that baggage handling consists of 4 sub-processes, 1, 2, 3, 4, that happen along the timeline. So this is our timeline. Inside an in-zoom process, the timeline flows from the top of the diagram, or of the ellipse, to the bottom. So what we see is that we have origin baggage handling, which involves the origin airport, which is a specialization of a generic airport. There is a destination baggage handling that happens at the destination airport, which is another specialization of airport. There is the airline involved, and the airline, among other things, consists of the lost and found desk, and the baggage, remember, has an attribute baggage location. We saw the origin and destination states because these were the only ones relevant at the abstract top level. But now we add 2 more states, which are the aircraft and other, which is any place other than the origin or the aircraft or the destination. That's when it unfortunately gets lost, right? So we start with the baggage location of the baggage at the origin. This is the input state. We do origin baggage handling, and it can end up, hopefully, at the aircraft, but it can also end up in some other location. Then the next process takes place where the destination baggage handling takes the baggage location from the aircraft and puts it, hopefully, again, in the destination. But I'm missing here a link. Well, no, that's good. Once it's, if it's done and we are in the destination, we are good to go. So then there is baggage claiming, in which the passenger is involved, and if the passenger retrieved her luggage, then he leaves and everybody is happy. But if not, then there is a lost and found baggage handling, in which the lost and found desk is involved as agents, and this happens only on the condition that the location of the baggage is other than the origin or the aircraft or the destination. So you'll start to get the picture, and this can be simulated by execution of this model. So you will see graphically how red dots move running along this from this when this happens, and then this happens, and depending on whether we got it into the aircraft or another place, either this or this will happen, and you can follow and track the system exactly through the stages of the execution. But this is not the end of it. You see, wherever you see a bold line process, that means that there is yet another level of detail. So origin baggage handling is one of those, and this one is another one. So similarly, we zoom into the origin baggage handling, and now we see that it consists of checking in, then security screening, which can result in an object called security clearance obtained, which has either a no or a yes outcome. If no, then there is another security. If yes, it goes on to sorting and loading, which in turn, as you can see by the bold line, has yet another level of detail by zooming into this. So I think you get the picture. I'm not going to. And then again, zooming into sorting and loading, which is here, you can see. So we go really to the fine details of where the baggage is located and whether the baggage holder is the security or the airline, and whether security clearance was obtained, which is the condition for this to happen in the first place, and so on and so forth. And if this is not enough, we can do yet another zooming into the baggage sorting and ad infinitum. Of course, there is always a situation where the modeler has to decide when enough is enough. You can go on, and it depends, of course, on the objective of the modeling. So in 2008, INCOSE created a task. INCOSE is the International Council on Systems Engineering, created a task force that came up with a list of the 6 leading model-based systems engineering methodologies as opposed to languages, and OPM was listed as one of them. And the plan is that in May of this year, it is expected to become an ISO standard when in Frankfurt there will be a meeting of the Technical Committee 184 Subcommittee 5, who has been doing this over the past 6 years with my involvement in it. So the next question is, what model-based systems engineering languages are out there? I already mentioned, or maybe not, UML, which is Unified Modeling Language, is the object management group, a consortium of the large software companies. This is a standard language for modeling software, and it has 14 diagram types in its current version. There is SysML, Systems Modeling Language, which is the OMG, the same consortium, standard language for modeling systems. It's a profile, a derivation of UML, which predates SysML, and it has only, quote unquote, 9 diagram types. By diagram types, I mean something like object process diagram, but a totally different set of symbols and concepts that are supposed to give you another aspect of the system. And so imagine not just 2 such families of symbols, but 9 or 14. But this is what it is. OPM is the object process, is in the process, as I mentioned, of becoming ISO standard. It has 1 diagram type and an auto-generated text that comes along with it, as I've shown. So it's not that SysML is 9 times more complex than OPM, or UML is 14 times. It's much more, because there are interactions between the diagram types, and the complicatedness grows exponentially. So we have already seen that there are 2 modalities, the object process diagram and the object process language. So just to summarize, OPM unifies in a single model function, structure, and behavior, as we've seen. We model objects and processes that can be hardware, software, regulations, humans, molecules. Processes could be chemical reactions, fusion of subatomic particles, and so on. And the B-model expressions through graphics and text. And the small alphabet really consists of stateful objects and processes that transform them, and a set of structural and procedural links. So now we get, having seen the baggage handling system, how am I doing on time? 5 minutes? 10 minutes, good. Okay, so what do baggage handling and molecular biology have in common? So we know that biology deals at the macro level with organisms which have organs, and the organs are made of cells, specialized cells for each type of tissues, and each cell in turn is very tiny, and inside the cell there are thousands of biological pathways and molecules that take part in these pathways and molecular reactions, biological, such as the one displayed here, just for representation. And with respect to resources on OPM, it's just digressing a little bit, is there is this object process methodology book that came out about 10 years ago now. A new version edition is upcoming, hopefully this year. There is a website of our laboratory where there are many resources, papers, journal, and conference papers, and descriptions of the projects that we are doing, and there is this standard that I mentioned that is in the final stages. A recent paper that was really published just exactly less than 2 months ago in PLOS One, Public Library of Science, which has become a very prominent journal in the last few years, is titled Conceptual Model-Based Systems Biology, Mapping Knowledge and Discovering Gaps in the mRNA Transcription Cycle. And really, this is the first paper that coins the term conceptual model-based systems biology. So systems biology has been around for, I would say, about 10 years, a decade, but conceptual model-based systems biology, you can think of this paper as a paper that is really starting this field of research. And this is just the citation. And it was really published, as you can see, in December 20, just a couple of months ago. And as you can see, pretty quick. This is what PLOS One prides, that they have a very fast round. So since August, within 4 months, which is really quite remarkable. So what is model-based systems biology? We have this research paper and experimental finding that I mentioned earlier, and from them we generate a computational model. You can think of an OPM model as a computational model. This computational model represents all the experimental findings that are documented in the published literature. And this can undergo model execution. So as I mentioned, this is how you would see the colors changing. So in this particular screenshot, this process in the background is happening, and within it, this first sub-process is happening, and it is going to affect all the objects that are linked to it. These objects are particular molecules. So this is basically a qualitative model. It doesn't deal yet with concentrations or gradients of concentrations or temperature changes or things like that, but it does tell you in no uncertain terms exactly what molecule is input in the process and which one, how its state changes, or whether it is dissociated into 2 other molecules that are generated in the process, and so on. And this, by doing this simulation, we do a comparison to the research papers and experimental findings, and often we find knowledge gaps, as I will mention. So stage 1, if we summarize this, we verify that the computer simulations that are done this way are compatible with the experimental results that are obtained in the lab. And usually they are, but sometimes not. This is one research cycle that goes on. But now we can suppose a new finding, a new paper just came out, and it asserts, based on experimental findings, that there are new facts that can be now incorporated into the model. So we add a new biological fact, or it could also be a conjecture of something that we think might be the case. And again, we update the model, and we do model execution as before. And if this validates the finding, fine. If not, it points out that there is some problem either with our model, which we have to go and fix, or if we are certain that our model is correct, then there must be some problem with the findings. So what happens is we can do conjecture evaluation and finding knowledge gap and designing and doing new wet lab experiments as a result of this process. So we really have developed, and this is real life, not a toy story of the baggage handling system. This is what happens to mRNA qualitatively. We start with the mRNA life cycle, which has 2 sub-processes, decay and nuclear import and transcription. And you see the major molecules that are involved in this. Now this, so you can see that these two sub-processes, each one in turn zooms into another level. So decay and nuclear import looks like this. You have deadenylation and decapping and degradation and decay zoom import. All these are, of course, biological terminologies that are taken directly from biological jargon. Any biologist would identify them immediately. We are not biologists, so we look at it as if it were Chinese. But these are all very common to biologists. These are their bread and butter. The problem is what happens in the, so you see here the hierarchy of diagrams of in-zooming. So this is just, before that we saw this one. This is the system diagram, the top level. Now we move to the second one, which is SD 1.1. You see the one in blue here. So imagine going through 1.1.1 and then more and more and more and more. And we have, this one has 11 levels of depth. I think I have it here, yeah. An example from level 10, OPD. And what we see is the same story. Objects and processes, okay? So they are self-similar. No matter at what level of abstraction you are, you still are going to see objects and processes all along the way. So think of it as fractals, okay? In fractals, you have some pattern, and it is copied, albeit on a smaller scale, recursively until the end, until it stops. Here it stops, in this case, at level 10, but it could be more, could be less, depending on the case. This is another example of a diagram. So what we actually, so we ended up with a really quite big model with several hundreds of objects and processes and about 100 object process diagrams, all interconnected in a pyramid hierarchical structure, all aware of each other, such that you can, for example, ask, show me all the diagrams where this particular molecule is modeled, and so you can follow and see and make queries and start to and follow things and try to understand what goes on. So during the process, we found knowledge gaps, which are defined as lack of knowledge regarding an object or a process in the system, and we found 22 knowledge gaps as a result of executing the model. They are documented in the papers. Moreover, we found 2 pairs of papers that contradict each other. This is something you can never tell. Even the most expert biologist could not, by being given a pair of papers, to tell whether, unless he really spends, a lot of time and trying to somehow internalize what each paper is saying, and even thus, this is dubious. By modeling it, you actually see that these 2 papers are claiming opposite or contradicting facts. And this can be an indication that one of them might be wrong, and maybe they have to go back to the lab and do yet another test to see whether the problem is in one of them, or maybe we made a problem. We have a problem with our model. Another thing that can be done with this is to assess conjecture. So what biologists do when they do their experiments, they find facts, okay? So here is the fact, what is the mechanism? It's not enough to give a list of hundreds of facts. You want to be able to decipher the underlying mechanism that brings about this set of outcomes. So what we did in this regard is to augment the model with one or more conjectures and iteratively improve the model with the conjecture so it fits the findings of the lab until it was satisfactory and it really reflected all the outcomes that are documented in the literature. This way we can claim that at least for the current findings, our mechanism that is represented by the object process model is really what happens. Unless or until a new finding will be found that does not fit into the model, or maybe has to make it more complex than it already is. And it remains to be checked in the lab whether this is indeed the mechanism, but at least it meets all the requirements or all the findings that have been found to date. Also, it can be used for experimental design, so we can call it in silico experiments. You say, what happens if we eliminate this material, but we don't do it physically in the lab? We just disable or change the state of some molecule to be absent, and then try to execute the model and see whether taking off or suppressing some kind of material or molecule, what does it do to the mechanism? And this way you can predict system behavior under varying conditions. And then again, to be verified fully, it has to be done in the laboratory, unless we are confident enough in our model that we can say almost for sure that, okay, you can save the time and money of running this. This is what's going to happen if you eliminate this material, which is, of course, very beneficial, because you can then accelerate biological research by maybe even an order of magnitude by saving the time and resources that are required to do this. Okay. Last, just as a teaser, I came up with an idea which I call COVERN, which stands for Computer-Based Augmented Virtual Environment for Realizing Nature, where there is a cave technology which is embedded in this, where you can visualize molecules in human size, and by using this OPM model as in the backstage, project the various molecules and how they interact, and humans can actually stand and touch them and feel, using haptic technology, how the forces happen and what happens. This really sounds like science fiction, but my hope is that one day we will be able to materialize this, because at least we have half of the technology, which is the conceptual modeling, and the cave technology is also quite well advanced, but it still remains. We already did experiments of displaying molecules in a cave, and we've done that in University of Aachen in Germany, who has the most advanced cave in Europe. So we have at least done a small step in this direction, but we are not there yet. This is just my imagination, which I created in this picture, but it's not so far-fetched. Here is another one. Okay, so in summary, we've seen that stateful objects and processes is all that is needed, sufficient set of entities to model complex systems in any domain and at any level of complexity. And that science and engineering are both about systems. So we've seen an example of a system, engineered system, the baggage handling, and a system from science, biological science. And they're all about systems, and they both consist of objects and processes, and how the processes transform those objects at various levels of detail. Science strives to understand by reverse engineering, and engineering strives to design and build new systems so that they provide value. Now that OPM is becoming a first ISO standard for conceptual modeling language, is an opportunity to adopt it as a universal modeling language in service of both science and engineering. Thank you.
So I think we have time maybe for one or two questions.
Yes, please.
How do you capture the flow of time in something that is meant to model processes which inherently have a time factor built in?
Right. So we can model processes that happen either sequentially or in parallel or conditionally, based on whether certain objects are in certain combination of states. So I didn't show it here, but for example, if we take...
It's okay. If you have provisions for that...
Yes, we do. Yes, please.
As I guess you know, there's a number of ontologies that have been developed for organizing data, so that data have different attributes associated with their
Right.
location and other features. Have there been any efforts made to try to coordinate the ontologies that you use in OPM?
Well, yeah, actually what I've been talking about is all about the ontology of the world. It's the generic ontology. Usually when people talk about ontology, they relate to a certain field of research or of a human endeavor, such as medical sciences or military or banking, finance. So each of those domains has their own ontology. What I'm claiming is this is the underlying basic ontology from which you can diverse into the various domains, each with their own ontology.
I guess my question had more to do with once you get to making the model quantitative, might there be the ability to automate the linkage of associated data if you were to match?
Right, absolutely, yes. We have a this is at the class level, but say if you want to model a university such as Dartmouth College, you have an object called student, but there are 6,000 students, so there would be 6,000 what we call instances of the student class, each with the values of names and attributes and the grades and what courses they took and so on and so forth. And you can then run a simulation of the university with its departments and professors and students going about their business. Okay, yes?
I had one observation regarding the baggage handling system.
Yes.
You designate the passenger as the beneficiary. I designate them as the victim.
It's true. It's true. They hope to be the beneficiary sometimes, but you're right. Okay, thank you so much.